Hi, my name's Steve Olson. I'm here to go over the State Aid Bridge Office's Timber Box Culvert Load Rating Guide. And I will step through a few documents here. So let's start with the housekeeping. So I'd like to go over a few introductory items as part of this load rating rollout. Go over a timber box culvert converter spreadsheet that we're using to create an equivalent cast in place concrete culvert, which BRR can run and convert the timber into that. Go over the guidance document. And then at the end of the guidance document is a rating example problem I'd like to go over as well. So the resources available to you when you're load rating timber box culverts in Minnesota for Dave and Moises are the old standard plates that were put together in the 40s and updated in the 60s. There is the 40-page load rating guidance document, and then the timber box culvert converter spreadsheet. And of course, your best guidance comes from Dave and Moises. Given the choice, the first choice would be to complete your load rating inside BRR and include the 2-page converter document from that spreadsheet in your submittal with the RCCL form. That will allow those coming after you to understand why you picked the rebar you did and the spacing you did for the BRR model. Second choice is if it's not appropriate to use BRR, you can use a physical inspection rating. If you've got some unique corner details or the structure is exhibiting some distress, or simply has some poor shear details where you think that will control the capacity of the structure, you should go to a PIR. You've probably seen this table in the past in other guidance documents, but based on the main span code, there are 47 timber box culverts on the local system in Minnesota. Of those 47 timber box culverts for the main span, 36 are 2 spans and 11 are 3 span structures. And there probably are several timber box culvert extensions on other types of culverts that are out there. So there could be some old CIP structures with timber extensions for road widening, things like that. Essentially what we're doing with this, since we can't model timber box culverts directly in BRR, is we are taking the flexural capacity of our timber elements and converting it to a concrete section. And so we take our bending stress, allowable stress, put some adjustment factors into it to get to a strength capacity for an LRFD capacity, if you will. Figure out what our section modulus for the roof or the wall is on a per foot basis, and compute our flexural capacity by multiplying the section modulus by the stress at strength. We then take that moment, and then given a section depth and size of reinforcement, we work backwards and figure out what the spacing of our reinforcement should be to give us the same flexural capacity. One heads up for you pertains to the density of the concrete we should be using in our converted model. If we're trying to get the dead loads right, we would use the same wall thicknesses as what we have in the timber structure and we would use a density of 50 pounds per cubic foot. Because BRR won't allow us to ignore shear, and here's the email from the BRR people saying there is a bug in the software, we've elected to double the wall thickness of our elements to take shear out of the controlling element, if you will. And when we double the wall thickness, our timber, which was 50 pounds per cubic foot, needs to be modeled as 25 pounds per cubic foot for the dead loads to work out properly. So next I'll step through the spreadsheet, which we have to get us our input values. So here we go. The converter spreadsheet, the most recent version is September 2nd, 2022. We've got 3 tabs on the bottom. We've got the general input and output. We've got the old standard plates for your reference, and then we have adjustment factors, reference information for the different adjustment factors to get from an allowable stress to an appropriate LRFD capacity, if you will. So we are expecting that people will print out the input and output parts of this first tab as documentation to go with their analysis run. And so our example is a 7'9" by 6 foot tall single cell, 1.85 feet of cover over the top. We've got an allowable bending stress of 1600 psi, allowable shear stress of 170 psi, and those values came from the bridge design manual. We have barrel width and height dimensions, we've got wall thicknesses, and we've got top and bottom thicknesses for our example problem. Over on the right hand, for reference, we do have the standard dimensions from the standard plates, and they vary from a 3x3 box to a 5x7 to a 6x6 is the typical range for a standard timber box culvert based on the plates. Going further down, our converter assumes the concrete culvert will use 4 KSI concrete, and it assumes that a rebar strength of 60 KSI will be used, and that's what the converter assumes will be used. The user has the ability to change the size of reinforcement and the clear cover to get the reinforcement placed properly. So for this example, we've assumed a number 5 bar, 1 inch of clear cover, and then so the center of bar is 1.31 inches away from the tension side of the section. Here are the modifying factors to get us from our allowable stress up to a strength stress. And so the allowable factors or modifiers are here, and the adjustment factors, more information can be found on the 3rd tab. So from a flexural capacity, we've taken our 1600 or 1.6 KSI stress, run it through these multipliers, and arrived at a 3.83 KSI strength capacity for our timber. We've computed our section moduluses for the wall and the top and bottom to be 50 or 72 inches cubed per foot. Multiplying things out, our stress times our section modulus, we get a flexural moment of 162 or 13.5 kip feet per foot for the walls. And because our top and bottom slab are thicker, we get a bigger moment capacity for that timber as well, 19.5 kip feet per foot. If we truly could ignore shear, we could step through with an equivalent wall thickness, and then this would be our D dimension, the 1.31 inches plus 3.69 gives us 5 inches for our walls. 4.69 plus our 1.31 gives us the thickness of the top and bottom slab. And so we would need this amount of steel per foot. And since we're using number 5 bars, here's the spacing of those bars. But because we can't ignore shear, we need to double our wall thicknesses. So instead of 5, we've got 10-inch walls. Instead of 6 inches top and bottom, we've got 12. So our D dimensions increase, and then our wall areas of steel drop per foot. So from 0.92, we're down to 0.39, 1.04 inches squared, we're down to 0.46. And so when we get to our example, we will have wall bars that are sized at number 5 with 1 inch clear cover at 9.54 inches. And our top and bottom bars will be spaced at 8.15 inches. There's some checks down here to show you how close we get to our target capacities, if you will. And then there's a reminder that you need to explicitly set impact equal to 0 for all of the vehicles that you are load rating. BRR assumes it's a concrete culvert and that impact should be applied or dynamic load allowance should be applied. Timber culverts are not amplified with impact or dynamic load allowance, so these values need to be explicitly set to 0. So that is our converter spreadsheet. We basically give it an input bending stress, some wall thicknesses, and it will give us thicknesses and spacing of bars to be used in BRR. Now that we've stepped through the spreadsheet, we can step through the load rating guidance document. And so it's a 40-page document. And so we've got a table of contents, and then we've got a couple details from the standard plates to give people an idea of what the typical details look like. We've got an introduction, and we talk about trying to figure out the best way to load rate the box culverts. We tried to do it outside and process the data in Excel spreadsheets, and that ended up with tens of thousands of lines of data to handle. And so it was much simpler to convert our timber to a reinforced concrete member than to process all the data and quality check all that outside data as well. So that talks about using the process described in the guidance document. We've already talked a little bit about the timber box culverts on the local system. The standards are standard plates 3060 and 3061. They were first introduced in 1941, and the last revision date we could find was 1966. They were designed to have 2 to 8 feet of fill over the top, and the wing walls were rotated 30 degrees from the alignment of the walls at both ends. Here's the table I highlighted in the converter spreadsheet showing the typical dimensions for the timber box culverts. One of the notes on the standard plates that we were unfamiliar with when we started looking at them was all timber to be 1,600 pound F or better. And after discussing this call out with several experts, we're pretty sure it meant an allowable bending stress of 1,600 psi or more should be the grade of timber utilized in the culverts. If we look at the current MnDOT Bridge Design Manual, we will see that the values presented for beams and stringers, select structural Douglas fir larch. We've got a bending stress of 1600 psi or 1.6 ksi, and a design shear stress of 170 psi, and a modulus of elasticity of 1600 ksi. To sort of put those values into perspective, I included a chart from a 1914 handbook by Milo Ketchum, where he grabbed the 1909 railroad spec chart on timber, and it calls out the following values. And so it's not labeled Douglas fir larch, it's labeled simply as Douglas fir. So we might be looking at a slightly different material, but the modulus of elasticity is listed as 1.5 million psi and a safe bending stress of 1200 and an ultimate bending stress of 6100 is the average ultimate. And if you remember from our converter spreadsheet, we were using 1600 for the bending stress. And once things were multiplied up, we were at 3.83 KSI, so still well below this extreme fiber stress for ultimate. They're showing a shear stress of 110 PSI here as opposed to the 170 we're using in our example problem. So it was helpful for me to see that these average ultimate values are still significantly above what we're using in our converter for the flexural capacity. One of the things we also learned was that there was a bust in the shear stress values presented in the AASHTO standard specifications for bridge construction. So when you look at the Douglas fir larch and you go select structural, beam, and stringers, we're at 1600 psi for bending, but we're only at 85 psi for shear parallel to the grain. And so what we learned is that when these values were assembled for the standard specs, a reduction for checking was applied twice. And so these values are lower than they need to be. And we see the modulus of elasticity value at 1.6 million psi is what we expected to see. Moving ahead to the AASHTO LRFD bridge design specifications, we can go into Douglas fir larch again, go to select structural, look at beams and stringers, and we'll see our 1.6 KSI bending stress, and back to the 170 PSI shear stress for parallel to the grain, and the 1.6 million PSI modulus of elasticity value. So what that means is that if you have a culvert or a timber element that was controlled by shear and it was designed by the standard specifications, you probably have more reserve capacity in those elements than what the designer intended. We also looked at for span lengths between 2 feet and 12 feet, and that's well beyond the 3 to 7 feet listed in the standard plates, to try and figure out if flexure controlled or shear controlled for these span lengths. And essentially what we found is that you needed a span length less than 2.25 feet for the 4-inch roof to control, and that if you had a 6-inch roof and you got to 4.25 feet of span, you would be controlled by flexure. So based on this analysis, we were comfortable focusing on the flexural capacity and not the shear capacity of the timber elements. So like we talked about, we're using a conversion process to take the timber to an equivalent reinforced concrete section. BRR had trouble ignoring shear, so we need to double our roof and wall and floor thicknesses and then take half the density of timber to get our dead loads to work out properly. So we went over the converter spreadsheet, and here is the guidance for that in the guidance document. So we've got the 3 tabs. We talk about each of the tabs. Here's the input. We've got a sheet that describes each of the input fields and whether or not it is used for the conversion. Then the next page has the output, and so here's the output values. And we're going to be using the 9.54 and 8.15 inches when we get to our example. But here's the output value, and similarly we have definitions for each of the fields and what they mean. So items in red refer to a double wall thickness. Items in black are the same wall thickness. We are using a simplified calculation for area of steel. The equation built into the spreadsheet assumes 4 KSI concrete and grade 60 reinforcement. And here's the equation to compute area of steel. And it is in mixed units. So the units are a little squirrely. So moment is in foot kips and D is in inches. There are the additional tabs in the spreadsheet with the old standard plates and the guidance information on the adjustment factors. And the next part is the example problem, which for us is 5-inch thick walls and a 6-inch roof. We're going to double those to be 10 inches and 12 inches. We've got a span of 7'9" and a rise or height of 6 feet. And we've got an assumed cover of 1.85 or 1.845 feet. So here's our input values, and these look very similar to what you've seen already in the spreadsheet. And so we're using the number 5 bars. We've got 1 inch of clear cover, and the distance from the center of the bar to the tension face of the section is 1.31 inches. Here's our output fields, and so we are using 10 and 12-inch thicknesses with these bar spacings, 9.54 for the wall and 8.15 for the top and bottom slabs. There is a template for this example problem that is available from Dave and Moises. It should be on the state aid website, and it has this example included in it. So you want to start out and have a good description of your problem and what you've converted to get to the equivalent concrete section. So include a good description. And then we've got our culvert definition. And so we are using fill height of 1.845 feet. And then we're using the 7.5 by 6 foot timber 1 cell culvert. We are not using standard concrete because we're messing with the density and the modulus, and so its concrete is Douglas fir larch. And we are using a grade 60 reinforcing steel. Because this is a single cell structure, we are applying soil pressures from both the left and the right. We are going to go with a load factor rating method because the legal loads have a 1.3 factor with LFR versus the 2.0 factor with LRFR. With respect to the control options inside BRR, we want to have all the boxes checked except exclude bottom slab. And we recognize that ignore shear doesn't work properly. We still recommend checking it. We then put the culvert geometry in. So we've got a cell height of 6 feet. We've got a cell width of 7.75 feet. And we're putting our construction joints at the top or at the bottom of the slab, top slab here. Because the timber box culverts do not have moment continuity around the corner, we are modeling things with a moment release at the top of the walls and at the bottom of the walls. And we're assuming there is side sway support provided so that there is stability in the analysis model. We need to define our reinforcing steel that is used inside BRR. So we've got our grade 60 material. We're assuming it is a number 5 bar. We do the same thing with the vertical bars. And in our culvert segment, we are saying our concrete is what we've modeled for Douglas fir larch. Down in the culvert thickness section, our top and bottom slabs are 12 inches, double the timber, and then our wall thickness is double as well at 10 inches. Inside components in the concrete, we get to modify or confirm that we're using the right values for our concrete. So here's our density for dead loads at 25 pounds per cubic foot. And then we are specifying a modulus of elasticity of 1600 KSI. And this really should not impact things unless we're looking at multi-cell box culverts. On the culvert loads tab, we can set the depth of fill at the start and end of the section. And then our live load surcharge height for LFD should be set at the standard value of 2 feet. And so here's where the meat and potatoes come together. So we get to apply our reinforcement. So we are looking at the top slab bottom bars. So this is sort of our positive moment region, if you will. And so we are saying the clear cover is that 1 inch we talked about. And then we're saying the bar spacing is at 8.15 inches in and out of the screen. We do a similar exercise for the walls with the vertical bars. We've got 1 inch of clear cover. And here's that 9.54 bar spacing. We go into our analysis settings. We confirm we're looking at an LFD load rating method. We insert the rating vehicles we want to look at and have evaluated on the structure. And then we need to go into the advanced tab. So after the vehicles are in, otherwise this whole sheet becomes blank if we don't have the vehicles in yet. But once we bring the vehicles in and get them on the right side of the prior screen, we can hit the advanced tab. And then we need to go in and explicitly call out 0 impact for each of these vehicles. If we leave it blank, it will go back to the default value of impact for a concrete culvert. And so if you've got a lot of fill, there's not much penalty there. But if you have not much fill, you can have a 20-25% penalty by not setting these values to 0. After you get the impact and dynamic load allowance set to 0, you can run the rating, and you should get rating factors that are appropriate for each of the vehicles on the structure. So that concludes the example in the guidance document. There are a couple special topics we talked about. If you've got multi-cell timber box culverts, you need to be careful on how you handle those. If there's continuity for flexure over the interior walls, then you need to add reinforcement on both sides, top and bottom, for those. Otherwise, your multi-cells can be handled with a single cell. So you need to pay attention to that. Notched elements are another thing to pay attention to, where the notch, where the element is supported on only the upper part of the notch, you'll likely have substantially reduced shear capacity. And so we've included some guidance on how to deal with that. Breyer's text, Design a Wood Structure, has an equation where we can compute our capacities. And so the conversion spreadsheet allows you to look at some of the updated shear values, and then you can see what kind of a magnification effect you might have. And it's dependent on the ratio of the notch depth to the overall member depth. And we've got a couple final notes inside the guidance document. We recognize we're mixing methodologies here. We're using an LFD load rating in BRR along with an LRFD conversion of the timber elements. And we recognize that inside BRR, typically flexural capacity of reinforced concrete members is not terribly different between LFD and LRFD methodologies. And once the live load factor for legal loads is reduced from the current 2.0, we can be a bit more consistent and use an LRFD rating method as opposed to the LFD. We can talk a little bit about that here, and we'll be more consistent in the future once that factor gets corrected. And the guidance document concludes with just the standard plates for timber box culverts. And so those bring you to the end of the guidance document. So with that, I will conclude this video.